We've been looking up at the stars for a really long time, essentially since the dawn of humanity, because we want to understand what's going on in the night sky. However, there's a big limitation to how we can actually observe these things. You see, everything is really far away from us. The things in the sky are so far away from us, in fact, that they appear to us almost as single points of light projected onto just this big dome around us. And that means it's really hard to learn about the stars and planets we see in the sky. It's pretty hard to, send out a rocket with a piece of string to measure how far they are from us, for example, or to see how wide they are, or to determine any of these other things. If I look at this nice picture that I took, for example, how could I tell how far away these planets are from me, or how far away they are from each other, if I can only observe them from here on Earth? The only thing we can really do is try to understand as much as we can with the limited information we can gather from here on Earth. For example, I've got here a diagram of the phases of the moon, which was drawn by an Islamic scholar named Abu Rehan al-Biruni. Al-Biruni was trying to understand the phases of the moon within the context of just what he could see from here on Earth. And as equipment has gotten more advanced and sophisticated, the things that we can observe from here on Earth have gotten more sophisticated and advanced. And one of these things is light spectra. And from this has come the field of astronomical spectroscopy, which is what I'm going to be covering today. Spectroscopy as a field really started with Isaac Newton. He is credited, of course, with discovering that white light, such as that emitted from the sun, is actually made up of different colors of light. He did this by separating it with a prism and then recombining it with a prism and doing all sorts of experiments with it. He observed this spectrum of colors coming from the prism, of course, that is actually the visible spectrum of light. His findings on the spectra of light spurred on a new interest in the study of the spectra of light, specifically that coming from the sun. Joseph von Fraunhofer was someone who got really interested in this. He was actually trained as a glassmaker, and so he had the skills to make very pure prisms for the study of optics and spectroscopy. And he was able to build essentially the first modern spectroscope, which is a device used to view light spectra. He used this to do a lot of things, and one of these was to observe the sun. And when he observed the sun, he found that the spectrum of light coming from it had a lot of these dark lines in it. He counted 574 of them in total, and found that they were fixed on their position in the spectrum from day to day. He also observed the spectra of stars in the night sky using telescopes with his spectroscope, and found that they also had these dark lines, but that they were slightly differently arranged. As it turns out, these dark lines he was observing were absorption lines. What these come from is the absorption of very specific wavelengths of light by atoms. For example, I've drawn this hydrogen atom here. As it turns out, when a particular photon of a particular wavelength of light strikes that atom, it has a very specific energy. And if it's the right kind of energy, it will cause an electron that is orbiting this atom, well, orbiting in quotes, to jump to a different orbital. This absorbs that photon into the atom and causes these absorption lines to occur because all of those photons just aren't making it past. Stemming from spectroscopy came a lot of different discoveries in the physics world, not just related to astronomy, but many of them, of course, related to astronomy. Johann Jacob Balmer, for example, discovered a formula for predicting the emission lines coming from hydrogen. Hydrogen, which is what I mentioned here before, actually has emission lines when you heat it up or otherwise energize it, which are actually at the same wavelengths as these absorption lines. You see, once you energize it and it absorbs those particular wavelengths of light, it will actually re-emit them when those electrons go from those orbitals back to their lower orbitals. Later on, Johannes Rydberg created the Rydberg formula and extended these emission line predictions to other chemical elements by taking into account things like the atomic number. But neither Balmer nor Rydberg actually understood the mechanisms behind these formulas, and no one really did until Niels Bohr and the model of the atom. You see, he was actually able to use his model of the atom to derive the Rydberg formula and a lot of the constants within it. And he was able to describe the behaviors of these formulas very well in the behavior of orbitals and electrons. Bohr's model of the atom was actually created using some elementary quantum mechanics concepts, and later on, his concept of the atom was extended into what we now know as quantum mechanics. Spectroscopy was also key to discovering the composition of the sun. You see, in the early 20th century, the scientific consensus of the time was that the chemical composition of the sun and other stars was pretty similar to that of Earth. But Cecilia Payne-Kapuskin actually did a lot of observations and research and found that this wasn't really true. In her doctoral thesis, she applied the ionization theories developed by Meghnad Saha, who was an Indian astrophysicist, and analyzed stellar absorption lines from the sun and other stars using these theories, and found that stars such as the sun were made up mostly of hydrogen and helium. However, Henry Norris Russell, who was reading her dissertation, actually dissuaded her from concluding this because it went against the scientific consensus. About 4 years later, though, he realized that she was actually right about the sun being made up mostly of hydrogen and helium, and actually published something about this, crediting her specifically with discovering this. However, of course, because Cecilia was a woman, Russell actually ended up sometimes getting credited for this discovery instead of her. History blows, I guess. The final thing I'll be talking about in terms of discoveries is actually the expansion of the universe. Edwin Hubble was an astronomer who focused on very distant objects and stars in the sky. A lot of his work involved observing what he thought were clouds of gas or dust in the sky, but what they actually were galaxies beyond the Milky Way. So, as part of his work, he often observed the parallax of objects in the sky. Parallax is essentially the shift in the relative positions of stars in the sky as the Earth moves around the Sun. And this is used to calculate the distance of these stars in the sky from Earth. Hubble also calculated the redshift of stars and other galaxies in the sky using spectroscopy. Basically, he looked at the absorption lines of these and found that they were shifted from the absorption lines that should have been there from various known elements, and use this to determine the redshift, which is how much these wavelengths were shifted. You see, when things are moving away from us or towards us and they're emitting light, there's actually a Doppler shift that they experience that we can measure when we use something like a spectroscope. It's very similar to the Doppler shift you hear, for example, when there's a siren moving past you. And when he graphed the redshift velocity that he calculated from this and the distance from Earth that he calculated with the parallax, he found this nearly linear relationship that he codified in the Hubble's law. These findings, along with a lot of findings from other scientists at the time, led to the conclusion that the universe was actually expanding. In fact, we now know that the redshift of light from very distant galaxies isn't necessarily from the fact that they're, speeding away from us, but from how the light that is coming from them is actually literally getting stretched out because of the expansion of space and the universe. Now I'll be talking about some demonstrations and applications of the physics of spectroscopy. So spectroscopy often involves splitting light using prisms and other optical glass. For example, here I've got a picture of a prism and a spectrum that I managed to split from this lamp, and this is just a picture of some stairs in my house that had some light cast on them from the sun through a window. The reason that this occurs is because the index of refraction of light isn't actually completely constant for different wavelengths of light. It's actually dependent on the wavelength of light. For example, I have this Snell's law calculation for light moving and refracting through this prism. However, this N2 value isn't actually constant for all wavelengths of light. It's actually dependent on wavelengths of light and the color of the light because of that. And what happens is different colors of light will refract differently because of this. That's why Newton was able to split light through these prisms into different colors, and why the light on my stairs and the light that I set through these prisms split into a rainbow. Blackbody radiation is another concept very important to spectroscopy and physics in general. It relates the intensity of radiation to its wavelength. For example, there's a reason that the sun is mostly sending visible light and ultraviolet light at us rather than, gamma radiation killing us all. However, for the longest time we didn't really understand how this worked. We had the Rayleigh-Jeans law, which predicted that short wavelengths around the ultraviolet range, the irradiance of this light coming from a black body radiator would go to infinity. Obviously, this isn't happening because we'd be cooked and we'd be dead of cancer 100 times over if this was true. And eventually, someone found a better law. Planck, Max Planck specifically, derived using some crazy math and some thought experiments, essentially, this new law that described our observations much more closely. It creates these nice little graphs with peaks, and as it turns out, it also described what we know about stars pretty well. In this case, this is some data I have from the Sun. I believe it's the 1985 Verily survey of the Sun and its spectrum. And we can see that there are some absorption lines in it, but that it matches the shape of these graphs generated by Planck's law pretty closely and very nicely. So how do we actually use Planck's law to determine properties of stars and other objects? Well, we can use the Wien's displacement. If you do a lot of terrible calculus and use some Lambert W functions, you can actually relate the maximum radiance wavelength, which is the wavelength at which the maximum radiance occurs, such as here, it's around 0.6 micrometers, to the temperature of the black body radiator emitting that radiation using this constant. And if we do that for the Sun, I pulled out the max radiance wavelength using a spreadsheet program from that data and calculated this temperature, we can get some rough properties of the Sun and other stars. Now this is actually pretty off from what we think the Sun's temperature actually is. There's a lot of reasons for that, but it's actually pretty close. And if you do some proper calculations and project what we think the radiation from the Sun should look like, it actually matches what we've measured pretty closely, which I think is pretty cool. And as it turns out, if you do this sort of thing to more distant stars, it often works out pretty well anyways. So that's really all I've got to present for astronomical spectroscopy. I think it's really cool, and I think there's a lot of different fields of physics and physical discoveries that have come from it, and that's why I really wanted to explore it. I'm also going to be putting up actually a little appendix video on this, talking about the Rayleigh-Jeans law and how it relates to the Planck's law, so do stay tuned for that as well.